Hi, I'm Kyle Burns from the University of Glasgow, and in this talk I'll be showing what my colleagues and I have been working on to bring constraint programming to the field of bigraphs, and how we employed a subgraph isomorphism solver to solve complex and difficult bigraph operations. So bigraphs aren't really a thing you see often in constraint programming, and that's because they're used more as a data structure for systems modeling and verification. However, in a bigraph system, the underlying data structure undergoes matching, which is a very interesting variant of the subgraph isomorphism problem. The differences are you've got a much more complicated data structure, so you have a mix of directed edges, you have undirected hypergraphs, you have both induced and non-induced matching semantics based on the addition of additional abstract nodes and where they're located in the input. So what we've done is we've adapted a subgraph isomorphism constraint solver and encoded a bigraph structure to be able to be taken as input for this SIP solver, and we've added additional constraints to the solver so we can perform bigraph matching with it. And we found that this method it outperforms current state-of-the-art bigraph solvers by over 2 orders of magnitude, which we're pretty proud of. Not only this, but now that we have proven that it can work for bigraph matching, we also think we can apply the same method to other bigraph variants, so variants to the structure, as well as different bigraph operations entirely. So as a brief background, what are bigraphs? They're a data structure composed of 2 graph components that share the same set of entities. You have the place graph, which is a directed forest that defines spatial locality between entities. So are examples such as a person inside a room. You have the link graph, which is a hypergraph that rather defines non-spatial connections between nodes. So that may be something more like a wireless network of devices that they don't care where they are physically located, they're still connected. And just as a disclaimer, when we work with bigraphs, we add the sharing property, so the directed forest is instead a DAG going forward. Bigraphs are a compositional structure, as in you can build larger bigraphs from smaller ones, and you can do this by through the abstract nodes that are inserted, which are the regions, which are root nodes, and sites, which are leaf nodes, and you can connect the regions of one bigraph with the sites of another. And similarly in the link graph, you can do the same with open hyperedges. You can join inner and outer links to create one larger bigraph structure. And this sort of composition allows us to define bigraph matching, where we may want to decompose a bigraph to find some defined pattern bigraph alongside some context and parameter. A pair of bigraphs can define a reaction rule, and this a reaction rule defines a substitution from one sub-bigraph structure to another within a larger bigraph structure to represent a sort of change in state within that bigraph. For example, a person walking out of a room, which is why we need bigraph matching. Bigraph reactive systems use these reaction rules, a full set of them, and a given initial bigraph state to generate a transition system where we discover all possible reachable states of given an initial bigraph state and the set of rules which define what is allowed to react and change. And this can be used to model interactive and dynamic systems that evolve in time and space. So what are the problems with this approach to systems modeling? Well, to determine whether some smaller bigraph exists within the larger bigraph to perform the reaction rule and do the substitution, we have to do bigraph matching for every time that we apply a reaction rule. The issue with that is bigraph matching is NP hard, and it's currently solved with SAT encoding methods. And because we want to do this thousands of times a second as we generate a transition system, that's going to get computationally expensive really quickly. So state-of-the-art tools such as Bigrapher can only really support up to 200 bigraph nodes currently within delay-tolerant applications. Large-scale networks may scale up to the 10,000s if you wanted to accurately model a power grid or traffic system. So we really want to expand the scale at which these tools can model and be an effective system for modeling. So what do we propose? Well, this whole trying to find a smaller graph structure within a larger graph structure, hang on a second, isn't this just subgraph isomorphism? So couldn't we just represent the bigraph matching problem as some sort of variant or more constrained version of subgraph isomorphism and encode the bigraph inputs in a way that a subgraph isomorphism solver would be able to read in and solve the problem for us instead of relying on dedicated SAT solving tools. And we could also add solution filtering to support further extensions such as the sharing property. And this is what we propose. To do this, we use an existing state-of-the-art subgraph solving framework, the Glasgow Subgraph Solver, which is also developed within the University of Glasgow. So with that out of the way, we now go on to discuss how we actually encode the bigraph structures to be able to be accepted as input by the SIP solver. So we do this by first separating the bigraph into the place and link graphs, and we encode these separately and then merge them later on. So to begin with, we start with the place graph. So this is fairly simple to encode because it's already a DAG, so it's already fairly easy to put it through the SIP solver. The exception of this is these abstract nodes that exist. So these can represent many or no bigraph coming in and out of the bigraph structure that we're dealing with. So the way we deal with this is we strip them out because there's no real any way of matching abstract nodes. And the way we instead represent them is through unary degree constraints. And we can do this because in bigraph matching, for a pattern target pair to be a valid match, the in degrees and out degrees of both the nodes have to be equal to that for that to be a valid match. However, there is an exception though, because these abstract regions, the regions and the sites, these can represent, of course, 0 to many in degrees and out degrees respectively. So there's an exception here where a pattern graph node is the child of a region node, the equality constraint becomes greater than or equal, and vice versa for the site nodes where the out degree goes from equal to greater than or equal. We enforce this as a pre-processing step by comparing pattern target pairs and comparing their in degrees and out degrees, as well as whether the pattern is connected to a region or site, and we apply the appropriate constraint. And you can see that in this representation here, where we remove the regions and sites completely, and the degree constraint enforced on each node is dependent on whether it was adjacent to a abstract node or not. So this representation of abstract nodes as degree constraints works for the most part. However, it is slightly under constrained, and that's because of the case where you have a region with multiple children. And that's because regions with multiple children must encapsulate only and all entities of their parents when it undergoes decomposition in matching. So for example here, we can see that if we strip this abstract region node, with our current encoding, the A and B would consider this a valid match. However, that shouldn't be the case because you can't abstract the C and the D to this abstract region unless they are both both parents of both A and B in this case. So this is enforced as a post-processing step and is also handled similarly in existing SAT solvers. So that's just one extra step we have to take to make sure that it's a valid encoding. So the target place graphs, when we do the encoding, we basically make very little changes to this because the abstract regions are fairly irrelevant. All we really need to do is change them to dummy nodes, which are never really matched. The reason we keep them instead of stripping them is because their edges still count when we want to do the pattern target degree constraint checks. So that's how we encode the place graph. However, the Link Hypergraph is far more complex, and I think this was the difficult part of this project. So because while the place graph can just be seen as a DAG with some abstract nodes, and if we figure out how to deal with those, then it's easy to feed into the SIP solver. However, the link graph is, you have hyperedges, which have very many unique properties. For example, you can connect between one to many entities. A hyperedge can connect to the same entity multiple times. For example, up here you can see that it has a double adjacency to this B node. They can also have the open property, which means that they're able to be merged during matching, or they can be closed, which means that they have to be isomorphic in their matching. So how do you model this in a conventional graph structure? Is it possible at all? Well, it is, because There's a special property that each label or type in every entity of a bigraph has called the associated arity value. And what this defines is actually the number of adjacencies that every node of a given type must have in order to make up a valid bigraph composition. So for example, in this diagram, we can see that the arity of A is 1, therefore every node of type A will have 1 hyperedge adjacency, so on for the B nodes having 2 hyperedge adjacencies, and so on. So in other words, every entity of an associated arity value will always have n ports, and it must always have those in order to be a valid composition. And we can use this restriction on the hyperedges in order to find a valid encoding to model this behavior. And we do this by, so we begin with the open links as they are less constrained. So we model the open links by, for every port that an entity has, we inject an additional port node for each port of an entity. For example, for any node 31, we will give it 1 L node as a child. For the B nodes, we add 2 L nodes as children. So that's how we model the ports. We then model the hyperedges themselves as k cliques between all ports that a hyperedge occupies. So for example, to model this hyperedge of cardinality 3 at the top, we turn it into a 3 clique where there's 2 adjacencies to the B and 1 to the A, as in the bigraph. And here's a more complex example with multiple k cliques, and that's how we end up representing the hyperedges. So we use this clique idea, and the reason why this works is we can then we can flatten this port vertex and clique representation into our existing place graph encoding. This will accurately represent the bigraph matching property of merging, as you can match multiple smaller multiple L nodes to the one larger clique when you do the matching. This is intuitive because we're not requiring any more constraints on top of the SIP behavior. We just need to accurately change the input, and the SIP solver will do the rest. It's also fairly scalable for representing hyperedges, as we are only inserting n port vertices for every hyperedge of cardinality n. So we're not really expanding the problem space that much through this encoding. So that's how we do open links, which are fairly under-constrained. However, there's also closed links which exist in the bigraph, and we have to deal with these additional constraints. Closed links can only map to other closed links. Open links can't map to closed links. Many open links can still map to the one closed link because you can close it in the matching process, and closed-to-closed mappings must be isomorphic. So how do we do this? So we actually expand on our representation of the k-cliques. So what we do is we add closure vertices, which we label with alpha here, which all port nodes in each included hyperedge all point to. So if a hyperedge is closed, we add this to each clique where we have an instance of a closed hyperedge. We only map closure vertices to closure vertices, and we also add an equal degree constraint on these closure vertices to enforce the rule that only closed can map to closed if they are exactly isomorphic. So that ensures that they must be the same size and cardinality and also have the same general adjacencies to their given relevant bigraph entities in order for that to be valid. So that covers all the components needed to represent standard bigraphs as subgraph isomorphism, and just to cap things off, I've included a quick brief example of a full encoding from top to bottom that includes everything we've gone over so far here. So bigraphs with sharing, so this is an extension to bigraphs, as I spoke about before. Allows it to be a DAG instead of a forest, so that means entities can have multiple parents. This introduces even further constraints. For example, a transitive closure constraint. You can't compose a bigraph where a site also ends up as a region, which becomes possible when you're dealing with DAGs. A solution which involves this would mean that there's a cycle in the solution. We don't want that, so that's not valid. Shared sites must be dealt with in the same way we deal with shared regions. And we also enforce these during a post-processing step, and we believe that the fact that we are able to represent a variant of bigraphs with just the introduction of a couple of extra post-processing constraints means that our SIP solver representation of bigraph matching is fairly extensible and flexible, whereas making these changes to support variants in a SAT-solving algorithm would mean the whole encoding would need to be overhauled to deal with each specific instance. So after building up our encoding, we implemented this as an extension of the Glasgow Subgraph solver. However, we believe that any SIP solver which is able to support directed graphs, enumerating solutions, labeling nodes, should be able to equally support this encoding method. We also employed the no-good recording functionality that the Glasgow Subgraph solver has, as permutations of link nodes were being treated as distinct solutions by the solver. So we add a no-good recording for the place graph nodes and closure nodes in a no-goods upon finding a valid solution to ensure that any duplicate solutions within the context of bigraph matching were being filtered out. And this ensured that the return solution set of the our SIP solver matched that of existing SAT solving tools and allowed us to validate that our encoding was correct. So to measure the performance of our tool, we compared our performance speed with that of the SAT and pseudo-boolean solver that currently exists and built into Bigrapher. And we did this on over 10,000 instances, which were a mixture of large and small problems with both sharing and without sharing. We measure via the aggregate speed up, due to the nature of how the Bigraph solver will be performing thousands of these for a single transition system. So we want to do lots of these really, really quickly. So we want to measure how long it takes to do all at once if done in parallel. So in this case, we found that via aggregate speedup, we actually get a performance increase of over 100, which we're very proud of. And not only that, but in every single test case, we found that SIP outperformed SAT reliably. So we feel like this is a straight upgrade to earlier ways of dealing with this problem. We did some further evaluation as well. We tried adding neighborhood degree sequencing. We tried adding supplemental graph constraints to see if we could increase our performance further, but we found that this doesn't have much of an effect. The hardest instances for SIP were found to be unsat instances that tended to have many candidate solutions that failed once the search loop reached the checking constraints. So this sort of suggests that the performance gain that we see just comes from the encoding itself, which is smaller and then results in faster propagation. However, because of the way it keeps hitting these near solutions, it's wasting time. There's a risk of this performing badly on a less advanced SIP solver for hard instances. So as future work, we intend to investigate further the usefulness of propagation constraints and small conflict clauses to hopefully preliminarily work out that these instances are unsat instead of coming up with thousands of candidate solutions only for them all to get knocked back and eventually return an unsat. So in summary, we have proven that yes, we can turn bigraph algorithms and operations into encoding and encode them as regular graph algorithms to produce really fast and efficient solvers. So we want to know as well, is there any other bigraph operations that we can produce an algorithm for using this method? For example, bigraph equality to graph isomorphism. Can we do relative pushouts, which is very similar to finding the largest common instance between two bigraph structures? So can we reduce that to maximum common induced subgraph? The constraints-based approach also allows for flexibility and easy support for extending the bigraph structure. We could support local bigraphs, which supports local typing and the nodes. We can also support maybe directed bigraphs, which have directions and the hyperedges as well. And hopefully we could also support that with just small tweaks to our encoding and our solver. So thank you for coming to my talk. I really hope you enjoyed listening to the idea of bigraphs and the great potential constraint programming has for furthering research in this field. I really look forward to progressing my research and presenting it again, hopefully in the near future. Thank you very much.